Hello everybody, welcome back to North Country Ham. I'm going to go through some more of my study questions for the Element 4. I know it's been a couple weeks since I posted anything. Just been pretty busy with life outside of things, you know, my son in his senior year and getting ready to graduate and prom, and we just got done doing his Eagle Scout ceremony. So we've been pretty busy in the home life, so I kind of put some videos on hold, but we're going to do another one here tonight and get it uploaded and just do some more of the study questions, so let's stick around. Alrighty, well, appreciate you sticking around. We'll get right into the questions here soon, and it is the 2020 to 2024 Element 4 Gordon West study guide that I've been going through. I've still got some of the projects in the works that I've been had started and done a little bit of video on. The dual band dipole for the underside of my tonneau cover on the truck that I 3D printed. I'm still kind of working to assemble that. The automated satellite tracking system, that's still making forward progress. The pan and tilt assembly and everything is all built, but just playing around with the Arduino sketch to make it all kind of come together. So hopefully having that up and operational and make some satellite contacts for field day coming up in June. So that's the goal between a friend of mine and I on the project we've been doing. So with that, let's get into the Element 4 book. So let's see here. And there we are. Into our Gordon West Element 4 book. And we kind of left off a little bit ago on what receivers and with great filter chapter that we started on. That's the chapter we're on. Went through several questions so far. We'll go through some more tonight and continue on from there as things go. So let's get right into it. Our next question we got coming up here is, which of the following receiver circuits can be effective in eliminating interference from strong out-of-band signals? A front-end filter or pre-selector. B, a narrow IF filter. C, a notch filter. Or D, a properly adjusted product detector. An effective means of eliminating out-of-band image signal interference is with a front-end filter or pre-selector filter network. These filters are much wider than typical IF filters and roofing filters. A higher IF also separates the image further from incoming signal, thus easing the front-end filter requirements. The front-end filters are electrically close to the antenna input jack, as opposed to the IF and roofing filters, which are in the middle of the receiver selection. The front-end filters must be band switched when there is a band change. So the correct answer is A. So which of the following receiver circuits can be effective in eliminating interference from strong out-of-band signals? A, a front-end filter or pre-selector. All right, get right into our next one here. Which of the following choices is a good reason for selecting a high frequency for the design of the IF in super heterodome HF or VHF communication receiver? Make sure I got that in the Well, the light glare, just no matter what I do, the lights keep getting worse depending on how I change them. So A, fewer components in the receiver. B, reduced drift. C, easier for front-end circuitry or eliminate image responses. Or D, improved receiver noise figure. So the intermediate frequency IF stage in the conventional receiver is where much of the amplification occurs. Selecting a high frequency for the IF allows for improved selectivity with minimum noise. This allows easier to build front-end circuitry to eliminate image responses from nearby strong signals. So the correct answer is C. So which of the following choices is a good reason for selecting a high frequency for the design of the IF in a super heterodyne HF or VHF communication receiver? C, easier front-end circuitry to eliminate image responses. And last question on this page. What transmit frequency might generate an image response signal in a receiver tuned to 14.3 megahertz and that uses a 455 kilohertz IF frequency? A, 13.845 megahertz. B, 14.755 megahertz. C, 14.445 megahertz. Or D, 15.210 megahertz. An image frequency of the incoming desired signal may be plus or minus 2 times the IF. In this example, the incoming signal that is 14.300 megahertz and the local oscillator is at 14.755 megahertz. The incoming 14.300 megahertz mixes with a 14.75 megahertz, producing a different intermediate frequency of 455 kilohertz. And so does an incoming frequency of 15.210 megahertz. So you do 15.210 minus 14.300 equals 455 kilohertz twice. 15.210 megahertz would be the image frequency. Various technologies, including good RF input tuned circuits, can minimize the image frequency, thus minimizing the problem. Again, 15.300 divided by 0.45 plus 0.455 equals 15.210 megahertz. You double the IF to come up with the correct answer. So, or it should be plus plus on that one, so I misread the symbol. It looked like eyes are going bad. So the correct answer is D. So what transmit frequency might generate an image response signal in a receiver tuned to 14,300 megahertz that uses a 455 kilohertz IF frequency? The correct answer is D, 15.210 megahertz. Try to get my camera a little better here. So, next question. What is reciprocal mixing? A, two out-of-band signals mixing to generate an in-band spurious signal. B, in-phase signals canceling in a mixer resulting in loss of receiver sensitivity. C, two digital signals combining from alternate time slots. Or D, local oscillator phase noise mixing with adjacent strong signals to create interference to desired signals. The mixer in your new HF transceiver combines two input signals to produce an output signal that is equal to their sum or difference. Undesired phase noise at the local oscillator output may result in the potential masking of ultra-weak desired signals. Nearby strong signals will add this to the problem. especially during HF contests when the bands are full. Correct answer is D. So what is reciprocal mixing? The answer is D. Local oscillator phase noise mixing with adjacent strong signals to create interference to desired signals. So what kind of digital signal processing audio filter is used to remove unwanted noise from a received single sideband signal? A, an adaptive filter. B, a crystal lattice filter. C, a Hilbert transform filter. Or D, a phase inverting filter. The adaptive filter, found in a digital signal processing DSP circuit, removes unwanted noise from the incoming SSB signals. So your correct answer there is A. So what kind of digital signal processing audio filter is used to remove unwanted noise from a received single sideband signal? Correct answer is A, an adaptive filter. Jeez. There we go. All right. Move on to our next one here. I want to keep All right. Move on to our next one here. What problem can occur when using an automatic notch filter, ANF, to remove interfering carriers while receiving CW signals? A, removal of the CW signal as well as the interfering carrier. B, any nearby signal passing through the DSP system will overwhelm the desired signal. C, received CW signals will appear to be modulated at the DSP clocking frequency. Or D, ringing it in the DSP filter will completely remove the spaces between the CW characters. The automatic notch filter, ANF, on your new HF transceiver is designed to cancel an interfering steady carrier as the lid across town tunes up without listening. Some transceivers even have more than one notch filter setting. On single sideband 40 meters, 7 megahertz foreign broadcast carriers can drive you nuts until you let the automatic notch filter find the steady tone and block it. Or perhaps you have the local computer noise with the steady tone right on your favorite HF frequency. With the ANF tuned on, it will do the job, but if you are operating on CW or data, it is best to turn the ANF circuit off so it doesn't think the slow code message is just an almost steady tone to remove. The modern ANF filter will recognize CW that is faster than about 7 words per minute, but keep the ANF off during CW and data reception. So your correct answer is A. So what problem can occur when using an automatic notch filter to remove interfering carriers while receiving CW signals? A, the removal of CW signal as well as the interfering carrier. All right, last question on this page. What is the noise figure of a receiver? A, the ratio of atmospheric noise to phase noise. B, the ratio of noise bandwidth in hertz to the theoretical bandwidth of a resistive network. C, the ratio of thermal noise to atmospheric noise. Or D, the ratio in dB of the noise generated by the receiver to the theoretical minimal noise. Yes. So, for VHF and UHF weak signal work on single sideband and CW, you want to operate a receiver with an extremely low noise floor. The extremely low noise floor allows weak signals to be detected above the receiver's internal noise. A receiver with a good noise floor will yield nearly identical noise power when switched between a dummy load and an antenna. Measured 3 dBs, the desired signal power plus n/n signal tone at 500 Hz and 2400 Hz. This works out to be a ratio in dB of the internal noise generated by the receiver itself compared to the theoretical minimum noise that the best receiver in the world would generate. Up on UHF, where we do a lot of weak signal operation like moon bounce, this is an important consideration. But down on HF, atmospheric noise would drown out any slight differences in a receiver's own receiver-generated noise. So the noise floor is less important ratio to consider in the new HF transceiver. So your correct answer is D. So what is the noise figure of a receiver? Correct answer is D. The ratio in dB of the noise generated by the receiver to the theoretical minimum noise. All right, move right now. Keep right on moving here. So our next question. What is meant by the blocking dynamic range of a receiver? A, the difference in dB between the noise floor and the level of an incoming signal that will cause 1 dB of gain compression. B, the minimum difference in dB between the levels of two FM signals that will cause one signal to block the other. C, the difference in dB between the noise floor and the third order intercept point. Or D, the minimum difference in dB between two signals which produce third order intermodulation products greater than the noise floor. When you're working a contest on HF and tune into a rare station just above the noise floor, you may hear that station request responses to transmit 5 kHz up. This is contest split operation, and it leaves the station in the clear without people calling right on top of his ultra weak signal. Powerful stations just a few kilohertz away will sometimes cause the weak station signal to disappear in the noise. Because your receiver is saturated with powerful signals nearby on the band, a receiver with good dynamic range will minimize desensitization when nearby signals blast your front-end circuitry. Blocking dynamic range is measured in decibels at your receiver noise floor. With AGC turned off and a nearby signal that leads to 1 dB of gain compression in the receiver, causing that weak signal to dip slightly into the noise, blocking dynamic range tests are more fairly calculated at 100 kHz off the desired signal. So your correct answer is A. So what is meant by blocking dynamic range of a receiver? Correct answer is A, the difference in dB between the noise floor and the level of an incoming signal that will cause 1 dB of gain compression. Okay, last question on this page. So what is the purpose of the pre-selector in a communications receiver? A, to store often used frequencies. B, to provide a range of AGC time constants. C, to increase rejection of signals outside of the desired band. Or D, to allow selection of the optimum RF amplified device. You may ask those big contest HF transceivers are so. You ask why those big contest HF transceivers are so large. On the inside, they may contain high Q, motor-driven pre-selector coils that can automatically track or may be manually adjusted to your desired receive frequency. These pre-selector coils may achieve a Q of over 300 and provide steep passband filtering not available with smaller fixed components or older external bandpass boxes. The peak of these optimal built-in pre-selector modules may even be adjusted away from your frequency to provide increased rejection of strong signals outside the band on which you are operating. The Q is so high that each pre-selector on each band needs its own micromotor drive assembly. But for big contesters, the big radio can really cut through the QRM. So your correct answer is C. So what is the purpose of the pre-selector in a communications receiver? Correct answer is C, to increase rejection of signals outside the desired band. Get situated here onto the next page. Okay. What does a third order intercept level of 40 dBm mean with respect to receive performance? A. Signals less than 40 dBm will not generate audible third order intermodulation products. B. The receiver can tolerate signals up to 40 dB above the noise floor without producing third order intermodulation products. C. A pair of 40 dBm input signals will theoretically generate a third order intermodulation product that has the same output amplitude as either of the input signals. Or D. A pair of 1 milliwatt input signal will produce a third order intermodulation product of 40 dB stronger than the input signal. All right. If you input two tones that are F hertz apart to the receive input, the mixer will output not only those two tones shifted down to the intermediate frequency, but also third order modulation tones of F hertz above and below the original tones. At normal input signal levels, these third order tones are much weaker than the original two tones, but as you increase the amplitude of the original two tones, the third order tones increase in amplitude 3 times faster than the original tones. If you continue to increase the input tone signal levels, at some point the signal strength of the input tones and the third order tones will be equal. This is called the third order intercept point. The third order intercept point of 40 dBm means that if your input tones were 40 dBm, then the third order tones would also be 40 dBm. The third order intercept point is not achievable in actual practice, as the receiver will saturate long before it reaches that point. So your correct answer is C. So what does the third order intercept level of 40 dBm mean with respect to receive performance? Correct answer is C. A pair of 40 dBm input signals will theoretically generate a third order intermodulation product that has the same output amplitude as either of the input signals. All right, and last question on this page. Why are odd order intermodulation products created within a receiver of particular interest compared to other products? A. Odd order products of two signals in the band of interest are also likely to be within the band. B. The odd order products overload the IF filters. C. Odd order products are in are an indication of poor image rejection. Or D, the odd order intermodulation produces 3 products for every input signal with the band of interest. Your new high-frequency transceiver boasts extraordinary receiver sensitivity, ultra-tight selectivity, and a 130 dBm odd-order intercept point. Odd-order intermodulation could occur in the receiver IF or RF stages when a pair of contest stations near you are hammering your front end just a few kilohertz away. Improved equipment designs minimize the odd order phase signals, or phantom signals, that are non-desirable weak signal products from these other 2 stations and are strong enough to interfere with the station that you are trying to tune in. Not only are you hammered by the 2 signals of interference, but also artifacts of their clean transmitted signals. Physically larger inductors in the bandpass filter stage may help, along with low distortion diodes in the bandpass frequency switching circuitry. Monolithic roofing filters, more expensive than overtone mode filters, will offer a better shape factor and less susceptible to intermodulation distortion with your top quality transceiver RF and IF stages. If you're considering a contest capable transceiver to feed into your 100-foot long boom HF antenna, the multi-$1,000 high-end HF transceivers offer the ultimate in rejection of odd order phantom signals with a distortion-free high dynamic range receiver system. So the correct answer is A. So why are odd order intermodulation products created within a receiver of particular interest compared to other products? Correct answer is A. Odd order products of 2 signals in a band of interest are also likely to be within the band. And I think that puts us at somewhere around our 10 or so questions for the night. So we'll end it there with that. Well, thanks again for everybody to watching and studying along with me. We'll continue doing this till we kind of get through all the questions. I'm still trying to push myself to take that next step and get the test taken and passed. I just haven't been ready there yet, or felt ready to take a charge at it. So, but I'm keep plugging away, and appreciate you studying along with me. And hopefully we'll get some more videos out there of some of the project builds too, to show progress on those. And I appreciate everybody stopping by and supporting. So with that, I'll say 7-3 and get on the air.